I want to add one more short piece to our discussion of interaction and animation, and that's the notion of being able to pick an object. And what that means is that we can point to something on the display with typically a mouse or some other device like that and identify not a position but an object and somehow uh, be able to use the position that's returned from the mouse to get that identification of an object. Now we're going to look at three methods for doing that. One is a method called selection that was supported in the fixed function pipeline on OpenGL. And we'll talk about how it's done and the possibility of implementing it in WebGL or any shader-based version of OpenGL. We'll also talk about a very popular method, which is using a buffer and the colors in that buffer to somehow link us to the objects that are being displayed, and a very approximate but very easy to implement method that's based on using a bounding box that the object fits into. So let's start with just an overall look at picking and say, well, why should this be very difficult? It turns out it wasn't very difficult in original graphics systems when we had big display processors, because what happened was if you had a device that used the really old input device of a light pen, then you displayed your what was in your what was called your display buffer or your display list object by object. And so if you knew the time at which the light pen had been triggered, you knew exactly where you were in that display file and could then map that into an object by just looking at what object you were in, whether you begin an object in all its primitives and ended it. That doesn't work quite that way anymore because of the way that a pipeline architecture works. We're not really doing it object by object, we're doing it triangle by triangle or line by line, and things aren't linked directly back to objects. We'd have to do that in our own code. There's also an issue of uniqueness, just being given a position on the display. There may be multiple objects that all render to that point, and so we have to be a little careful about which object we want. Generally, we're going to want the one that's closest to the viewer, and the one that, if we're doing hidden surface removal, is the one we'll see. But that's not necessarily always the case, and even if it is, we have to see how we're going to get access to the depth along with the position. What really complicates it is that the pipeline itself is forward. And if we look at what we're trying to do, that mathematically it's very simple to write down that if you have a transformation that takes you from a position in the object to a position on the display, it's an invertible transform under most conditions, and that you can then take a point in principle on the display and map it back into the object. But the problem is it's not tied very well to the forward nature of a pipeline. We're putting in vertices and we're getting things flying through that pipeline and displaying at very high rates. And to go backwards, which is a mathematical operation, can take a lot of time and just doesn't fit into that hardware architecture. So we need to take that into account. We also want to potentially take into account that exact positioning is very difficult to do. This is true of all interactive applications, that human is very error prone in that you can't get an exact position on a display, especially when it's a very high resolution display, to say it's exactly this pixel that I'm pointing at, or if I tell you which pixel I want you to point at, you're going to really be able to do it. The best I can say is that you can come close within some number of pixels, and we should take that into account when we're trying to do operations like picking that say, well, I don't necessarily have to be exactly on this line. Suppose we're trying to pick a line, an object like a triangle that's filled is much easier, but something like a line which may be 1 pixel wide is pretty difficult to point to, so I may want to have a strategy that takes into account that I may only be close to that line, and we'll see that in this discussion. But let's start on the first method, which is called selection, and as I said, it was supported by the fixed function OpenGL pipeline. And what it worked sort of as follows, that if you could, in your code, when you defined objects, now objects comprise a lot of different things. They comprise a lot of polygons, a lot of triangles, a lot of lines, a lot of points potentially. So an object is bigger than a primitive. But what I could do is assign to each primitive some sort of identifier, even if it's as simple as giving it an integer 1 for the first object, 2 for the second, and so on. So I can indicate for each primitive which object it belongs to. And if I build that structure up before I start rendering. Then as I render, the idea is that there will be a method of pointing to a place on the screen with the mouse, and then getting the IDs of those primitives that are near where the mouse is, and put them into something that's called a hit list. So every time I'm pointing at something, I'm hitting it, and that as I render, I generate this hit list, and then after the rendering, I can then examine the hit list and see which objects I'm pointing to, and if I've also in that hit list put not only the IDs but also depth information, I could say, oh, this is the closest one, this is the one that's furthest away. Now there are complications when I try and implement that, but the way it's generally done, and this is what was built into earlier versions of OpenGL, was to look at a window, not the window that you're defining for your whole scene, but rather a window that's a small area around the mouse. So everything that renders into that small area, we can assume is part of the object. So this is how I get around the problem of not being able necessarily to point exactly at a small object or an object that's very thin like a line. Now, what I can do is, as I'm rendering, I can keep track of whether a given primitive renders into this window or not. That's something I can do within OpenGL or WebGL. And then I could say, that's how I form the hit list, and then I could say, okay, which of primitives are in that hit list? Well, if I'm changing the window, and it's not the window that I really want displayed, then I don't want to display this rendering. Now, the way that was usually implemented is you used an off-screen buffer. In older OpenGL versions, you had the potential of having extra color buffers so that I could use one of those buffers to do this rendering into. And this is one thing you'll see. This is an extra rendering. Every time I do a pick, I will wind up doing an extra rendering by the most used techniques. Or if I didn't have an extra buffer, I could potentially clear the back buffer, render with this new window into that back buffer, forming my hit list. If I don't do a buffer swap, then I'm never going to see what I rendered into it. Then I could clear it and do my normal rendering after the pick operation, and then do a normal swap. So that was built in. It was fairly easy to do within Fix Pipeline. OpenGL, there were some helper functions in the GLU library to help you build that little window for whatever size area you wanted around the mouse. It's potentially possible, and I've seen some references to this, that people have implemented with off-screen buffers in WebGL. But what most people do is use the second technique, which I'll show you an example of at the end of this little lecture, of using color. So the idea is this, that there's a function that's still in WebGL that wasn't deprecated, as were many when we went to fully shader-based OpenGL, called GLReadPixels. That's sort of the best we have for going backwards. And what it lets me do is read a small block of pixels starting in any location I want. So we can say, okay, read one pixel. Let's take an idealized version. Read one pixel at the location of the mouse. That's easy to do. And what reading that pixel does is return the RGBA color at that point. And then the idea is to use that color to identify the object. Well, how do I do that? Well, if I do a rendering, if I have a simple rendering where I have, say, n distinct objects and each one is in a distinct color and I know those colors, then I could use that color to map backwards into which object has that color by just having a little table in my application. Now, the problem in reality is that many objects can have the same color. If I'm doing an application where I'm worried about what are the properties of the object, what are the material properties I want to use, something we're going to be talking about in a few weeks. I may be having the same materials used for multiple objects, and they're going to wind up displayed in the same color. So now I can't distinguish between objects just by color. More difficult is that if I use lighting, and so I have a model that combines the material properties of the surfaces with light sources in the scene, something we talked about at the very beginning of the course and we'll come back to in a few weeks, then I get all kinds of subtle variations of color called shades in the rendering of that object. Now I don't have a single color I can identify with that object. Well, here's a simple solution, is if I can do a rendering that I don't see, I can do a second rendering with a unique color assigned to each object. Now I can do what I'd ideally like to have is use read pixels to get a unique color for each object at the mouse location. So it maps back into a table, and then I'll say, okay, if it's red, therefore it's this object. If it's blue, it's this object, or whatever colors I want to assign. And you can do that with an awful lot of different objects. It's very easy to implement. We'll be implementing it later when we talk about discrete methods, because then we'll be talking about the read pixel function. And most people would rather do it that way just because it's pretty reliable. See, but it also requires an extra rendering. You're still rendering. What's different between doing that in the fixed function pipeline and doing it with WebGL is we're going to use off-screen buffers to do that, and that's one of the reasons I have to wait to talk about this technique later in the course. But off-screen buffers are very easy to set up and use in WebGL. Now let me give you one more sort of approximate technique that people can use, and this is very quick to do, doesn't necessarily require an extra rendering. What you could do is for each object, you can build an axis-aligned bounding box. Now what that is the smallest box rectangle where the sides are aligned with the x and y axes that the object fits into. Well, how do you get that? Well, all you have to do is compute the minimum and maximum x's and y's of all the vertices that comprise that object, and that gives you the corners of that rectangle, and that's really all you need to do testing of whether a point is inside or outside that rectangle. Now that's easy to do. We can do that by building a very simple data structure that's part of our description of the object. This goes on the application side. But you get little problems of it may not be totally accurate, so you get a couple of cases. So here's a point that's both outside the bounding box and outside our object. Our object here is just a simple triangle, and that's easy. So it's outside the bounding box, therefore it's something that if we return this location, it can't be in this object. Now if we look at this point, this is what we really want. This guy is inside the bounding box and inside the triangle, so we picked the correct object by looking at the bounding box. The difficulty is when we have points like this that are inside the bounding box, but they're outside the triangle. Now, this is going to register as a hit or a selection, and it's going to return the ID of this object, which could be a problem, especially if there's perhaps another object over here that this one's in front of. It's going to return this one, not the object that's over here that it's really pointing to. So it's an approximate method. It's easy to implement, and you can try that if you like. Most of us would use the color technique. Now let me show you the color technique, and it'll also show you some of the difficulties in doing this. So let's come look at this display. So here's an example I'm going to be using a lot in coming up. We're going to be turning to 3D geometry in the next lecture, and that's going to carry us right through the course. So here you see is a cube, which is sort of a standard object I'm going to be using to show various techniques. Here's the basic display. Now notice we've done the same sort of things. This cube has 6 faces. That means it's 12 triangles. We've assigned a unique color to each vertex, and using the default mode of letting WebGL interpolate colors across the triangles, we see we're getting all these shades across each of the faces of the cube when it's displayed. Now, I have the same buttons here, by the way. I can change the direction of rotation any way I like. I can also turn it off here. But what I'm going to do now is say, well, okay, I can't just now return by read pixels, return a pixel over here and use its color to identify which face I'm pointing to. Because look, it changes all over. Here I'm getting almost full green. Here I'm getting sort of the cyanish color in the middle. Here I have a very highly saturated blue. So I can't do it that way. But what I can do is re-render this to an off-screen buffer where what I've done that you can't see here is I've assigned a color, a constant color to each face, and I've used red, green, blue, cyan, magenta, and yellow. So now if I do read pixels on this off-screen buffer, now I'll get the color that I assigned to each of those faces. So I'm going to do that here, and I'm going to do it, it's just going to do a very simple thing. It's going to print out that color on the console log, and it also has we'll say if it's not one of those colors, therefore it's the background. So if I click over here, I should get something that says it's background and it's not part of the object. So let me click here, and it says that's the face I assigned to blue. And see, if I click any place on that face, I should get, notice it's telling me over here how many times I've clicked there. Now if I click on this face, it says that's the one that in the off-screen buffer I've assigned to magenta. If I click outside of the object, it's saying background. And when we talk about render to texture and rendering off screen later in the course, you're going to be able to implement this technique. But if you want to look at the code right now, it's in chapter 7 on the website. Okay, so what we're now is finished with interaction for now and animation. It should be part of all the applications and the assignments that I'm going to give you for the course. And now we can turn to look at really what I think is the core of the course, which is to look at geometry and viewing and material light interactions and texture mapping.